All right, welcome to another deep dive. Today, we're going to be talking about something that's really kind of mind-blowing, to be honest. We're diving into the world of how these large language models, LLMs as we call them, how they reason. You, our listener, have put together, wow, a seriously impressive collection of articles and research for us. It's a lot. And so our mission here is, well, it's a big one. It's to really understand how these AI models seem to think, what they can do, what they can't do, and the different ways this AI reasoning works. Oh, and of course, how we even try to figure out if it's really reasoning or not. Consider this deep dive, I guess you could say, your express ticket to understanding this whole LLM reasoning thing a little bit better.
Yeah, you've definitely assembled a comprehensive, really impressive set of materials here. I mean, there are articles here about chain of thought prompting, these broader pieces on the nature and limitations of LLM reasoning. Even that Reddit thread where people are debating whether we're overestimating LLMs and their abilities. There's this blog post laying out a framework for understanding what they call reasoning LLMs, that fascinating Google research piece that uses graph algorithms to kind of peek into transformer reasoning, even a basic explanation from Isera, just defining what reasoning in AI even is. And then there's that research survey called Beyond Accuracy, evaluating the reasoning behavior of large language models. I mean, it really is, it's a lot to dig into.
Okay, well, let's try to unpack all of this. I think our goal for you, the listener, is to take all this information and kind of condense it down into a clear picture. We want to be able to highlight the progress that's been made in enabling LLMs to do what seem to be complex reasoning tasks, but at the same time, we want to be very clear about the limitations, the stuff they still can't quite do. And we're going to be looking at some of the techniques that people are using to get these models to reason in more sophisticated ways, and also how researchers are trying to make sure that that reasoning is actually, valid, legitimate reasoning. So by the end of this, hopefully you'll have a much better understanding of how these LLMs tick without, and this is key, without getting completely lost in all the jargon, all that technical stuff. So get ready, because I think there are going to be some real aha moments as we start connecting the dots between all of these different sources.
Sounds good to me. So where do you want to start?
Well, I keep seeing this phrase pop up, chain of thought prompting. It's in a bunch of these articles. It seems to be kind of a big deal. So what exactly is chain of thought prompting, and why is everyone so excited about it?
Yeah, the interesting thing about chain of thought or code-to prompting is that it's all about getting these large language models to kind of show their work, right? You're basically asking them to think out loud. Instead of just giving them a question and expecting a one-word answer or a short answer, you prompt them to kind of lay out all the steps, all the logical steps they're taking to get to that solution. So the idea is if you can see their thought process, then they're more likely to get to the right answer, especially for problems that have, multiple parts to them.
So it's kind of like, if you think about it, it's like getting a student to show their work on a math problem, not just give the final answer.
Right.
So how is that different from like the normal way of prompting an LLM?
Well, with traditional prompting, you're mostly giving the model input-output pairs, right? So you show them questions and answers, but you don't explain how to get to that answer. With CoT, you're actually including the reasoning steps in those examples. You're demonstrating how to break a complex problem down into smaller, more manageable chunks. So the model learns not just the answer, but the process of getting there.
Gotcha. So you're not just teaching them what, but also how. Okay, so what kinds of tasks or problems does this chain of thought prompting, what does it work best for?
So from what I've seen in these sources, CoT seems to be really effective for tasks where the reasoning needs to be structured, step by step, like in mathematics, especially word problems, where the model has to do multiple calculations. It also works well for things like common sense reasoning, where the model has to use general knowledge to connect the dots. And in symbolic reasoning tasks, where they're manipulating abstract symbols and rules, CoT can even help with really advanced applications like complex decision-making, maybe even robotics.
Wow, so it's like you're getting the AI to narrate its thinking. And does this approach actually lead to better results? I know the article mentioned some specific research findings.
Oh, yeah, for sure. The research shows some pretty significant improvements in accuracy when CoTs is used with large models. Like, for example, with the GSM-8K benchmark, which focuses on math word problems, a PaulM model with 540 billion parameters, that's a huge model, saw its accuracy jump from 55% with normal prompting to 74% with chain of thought. That's a big jump, almost 20%. And with the SVMP benchmark, another math test, the improvement was even bigger, from 57% to 81%.
They also saw gains in common sense reasoning on the CSQA benchmark, and a pretty dramatic leap in symbolic reasoning accuracy from something like 60% to almost 95% with Coty.
Those are impressive numbers, especially those gains in math and symbolic reasoning. Those are areas where AI has traditionally struggled. But the article also mentions a catch. What's the main limitation of this chain of thought prompting?
The big thing is that Coty really only seems to work well with really big models. Models that have at least 100 billion parameters, those are the ones that see these huge improvements. It seems like you need that much capacity for the model to really grasp the multi-step reasoning that Coty encourages. In fact, when they tried Coty with smaller models, they often saw the model generate nonsensical chains of thought, which actually made the results worse.
So it's not a magic bullet. You need that massive scale for it to work properly. Okay, now let's zoom out a bit and talk about LLM reasoning more broadly. Why is reasoning considered such a fundamental capability for AI? Why is it so important?
If you really think about it, reasoning is what makes any system intelligent. It's the ability to process information, make connections, draw conclusions, and then use that to solve problems in a flexible way. And that's essential for almost every application of AI you can think of. Natural language processing, understanding language, computer vision, interpreting images, autonomous systems, planning and acting in the real world. Without reasoning, AI would be stuck just recognizing patterns without any real understanding.
And there's not just one way to reason, right? The article from Isra breaks down several types of reasoning. Can you walk us through some of the most important ones in the context of AI?
Sure. So Isra gives a nice overview. Let's start with deductive reasoning, which is drawing specific conclusions from general principles, like all men are mortal. Socrates is a man, therefore Socrates is mortal, that kind of thing. Deductive reasoning is used a lot in expert systems and rule-based systems. Then there's inductive reasoning, which is kind of the opposite. You start with specific observations and make general conclusions. For example, if you've only ever seen white swans, you might conclude that all swans are white, even though that's not necessarily true. Inductive reasoning is all about probability and is used extensively in machine learning.
Okay, those are the classic ones. What other types of reasoning are there?
Well, there's abductive reasoning. This is about finding the best explanation for something, even if you don't have all the information. Like if someone has a fever and a cough, you might guess they have a cold, even though other things could cause those symptoms. Abductive reasoning is used a lot in medical diagnosis. Then you have analogical reasoning, which is about making comparisons between similar situations, like saying that learning to fly a drone is similar to learning to fly a helicopter, that kind of thing. And of course, there's common sense reasoning, which is something that humans do effortlessly, but it's super hard for AI. It's about using all the everyday knowledge we have, like knowing that rain makes the ground wet. It's crucial for things like chatbots to be able to interact naturally with humans.
Yeah, common sense is definitely one of those things we take for granted. Are there other ways to categorize how AI systems reason?
Yeah, you can also look at the difference between monotonic and non-monotonic reasoning. With monotonic reasoning, new information can only strengthen your conclusions. It never makes you change your mind, like mathematical proof. But with non-monotonic reasoning, new information can make you revise your conclusions. So you might think a bird can fly, but then you learn it's a penguin and you have to change your mind. Non-monotonic reasoning is important for dealing with the real world where things are always changing. And then there's fuzzy reasoning, which is for situations where things aren't black and white, true or false. It's about degrees of truth. Like saying it's warm outside is fuzzy because warm is subjective. This kind of reasoning is used a lot in control systems.
Okay, so there are all these different types of reasoning, and researchers are trying to figure out how to make LLMs do them. How are they going about that?
Well, the LLM reasoning guide you provided talks a lot about prompting techniques. They're really crucial. And they divide the research into two main areas. Reasoning-enhanced strategies, which are all about crafting prompts that encourage the LLM to reason better, and knowledge enhancement reasoning, which focuses on giving the LLM more information to work with. Chain of thought prompting is an example of a reasoning-enhanced strategy, and there are others like active prompting as well.
Now, one thing that keeps coming up in our sources is this debate about whether LLMs are really reasoning in the way we think of it, or if they're just doing very sophisticated pattern matching. The paper, Can LLMs Reason and Plan, seems to lean towards the pattern matching side.
Yeah, that's a really important point. The author of that paper argues that, based on what we know right now, there's no real evidence that LLMs are actually reasoning or planning the way humans do. It's more likely that they're just really good at finding patterns in their training data and then reproducing those patterns when prompted. So it might look like reasoning, but it could just be very advanced pattern recognition. And as the paper points out, maybe we're mistaking that pattern recognition for actual reasoning.
That's a crucial distinction. So if they're not truly reasoning, where do these LLMs really fall short? The article about the limitations of LLM reasoning goes into some detail about that.
Right. So one of the biggest limitations is that they lack real understanding. They don't actually understand the concepts they're talking about. They're just predicting the next word in a sequence based on statistical patterns. So they're great at manipulating language, but they don't have the same depth of understanding that humans do.
Makes sense. So what are some of the other big limitations?
Well, another problem is contextual limitations. They can handle short pieces of context, but they struggle with long texts or conversations. They might lose track of information or misinterpret things, which leads to reasoning errors. And then there's the issue of planning. Many real-world reasoning tasks involve multiple steps, and LLMs often have trouble with that, like solving puzzles or coming up with plans.
And then there's that fascinating example in the article where LLMs try to answer problems that are actually impossible to solve. What was that about?
That's the water pouring puzzle example. Imagine you have a jug with 8 units of water and 2 empty jugs that hold 5 units each. The goal is to pour the water so that the first 2 jugs end up with exactly 4 units each. But that's actually impossible with those jug sizes. Yet when LLMs like ChatGPT were given this puzzle, they didn't recognize that it was impossible. They just tried to come up with steps to solve it, even though those steps were logically flawed.
So they were confident in their solution, even though it couldn't be done. But then the article said that if you change the jug sizes to make the puzzle solvable, they get it right. What does that tell us?
Right. So if you give them jugs that can actually hold the right amount of water, they can solve the puzzle.
Yeah.
But what's interesting is that it might not be because they're reasoning out the problem. It could be that they've seen similar puzzles in their training data, and they're just recalling the solution steps. So again, it might be more about pattern matching than real understanding.
And the last limitation they mentioned is something called state space computation complexity. What's that all about?
That's about problems where there are just way too many possibilities to consider, like planning a trip with multiple cities, flights, hotels, all that. For an LLM to try every single combination would be impossible. It would take forever. So they have to use shortcuts, these things called heuristics. But those heuristics might not always be right, which can lead to bad solutions.
So even with all their impressive language abilities, there are still some big hurdles for LLMs to overcome when it comes to reasoning. What are researchers doing to address these limitations?
One thing they're focusing on is improving the training data. By giving LLMs more diverse and higher quality data to learn from, they hope to create models that are more robust and have a better understanding of the world. And of course, they're continuing to work on techniques like chain of thought prompting to encourage step-by-step reasoning.
And what about using external tools or systems to help LLMs reason better?
That's another interesting area. Some researchers are looking at external verifiers, which are separate systems that can double-check the information produced by an LLM. And they're also exploring the idea of using specialized solvers for specific types of reasoning tasks, like math or logic. So it's like creating a team of different AI systems that work together.
Now, one of our sources, a paper on neural-symbolic learning and reasoning, talks about a different kind of hybrid approach. What's that all about?
So neural-symbolic computation is all about combining the strengths of neural networks, which are good at learning patterns, with symbolic AI, which is good at logic and reasoning. The hope is that by bringing these two approaches together, we can create AI systems that are both powerful and explainable, and that can overcome some of the limitations we've been talking about. This field draws ideas from a bunch of different areas, like computer science, neuroscience, even philosophy.
And what kind of progress has been made so far?
Well, neural symbolic systems have shown some real promise. One of the things they've been able to do is address the limitations of traditional neural networks, which are often stuck with simple propositional logic. These hybrid systems can handle more complex forms of logic, which allows them to reason in more nuanced ways. And they've already found applications in a variety of areas, like bioinformatics, control systems, even game development.
That's impressive. But are there still challenges with this approach?
Definitely. One of the biggest challenges is figuring out how to make these hybrid systems learn the underlying structure of knowledge from data. How do you get neural network to understand symbolic relationships? Another challenge is learning general rules from data. And then there's the whole issue of extracting knowledge from a neural network once it's been trained. How do you get those symbolic representations out? And a central problem that they highlight is something called the variable binding problem. It's about how neural networks, which work with fixed dimensional data, can deal with variables, which are crucial for symbolic logic.
So it sounds like a very promising direction, but there's still a lot of work to be done. Now, shifting gears a bit, the blog post on understanding reasoning LLMs focuses on building and improving what it calls reasoning models. How do they define that term?
Well, they define a reasoning model as an LLM that's really good at complex tasks that require multiple steps and intermediate reasoning steps. It's different from models that are just good at answering simple questions or retrieving information. It's about tasks like solving puzzles, doing advanced math, or writing code. Tasks that require more than just looking up facts.
And when should you use a reasoning model? Are they always the best choice?
No, not really. The blog post is clear about that. It says that you should only use reasoning models when you really need that multi-step reasoning capability. For simpler tasks like summarizing text or translating languages, using a reasoning model can be overkill. They're more computationally expensive, they produce longer outputs, and they can even introduce errors on simple tasks. It's all about choosing the right tool for the job.
Okay, so what are some of the ways that researchers are building and improving these reasoning models?
Well, they outline 4 main approaches. The first one is inference-time scaling. That basically means giving the model more resources during the inference stage when it's actually generating an answer. This can involve things like using prompts that tell the model to think step by step, or using techniques like voting and search to find the best answer among multiple possibilities. And while the DeepSeek research suggests that some of the simpler inference-time methods might not be that effective when built into the model itself, the blog post points out that they can still be helpful at the application level.
So making the model work harder to find the right answer. What's the second approach?
The second one is pure reinforcement learning. They highlight the DeepSeek R10 model as an example. This model learned to reason just by being rewarded for accuracy and correct formatting. It wasn't given any human-generated examples to learn from, which is pretty remarkable.
Wow, so it kind of figured out reasoning on its own, just through trial and error. That's fascinating. What's the third approach?
The third one is combining supervised fine-tuning with reinforcement learning. This is a more common approach, and the DeepSeek R1 model is a good example. It started with some data from the R10 model that it was fine-tuned on human-generated data, and then it went through more reinforcement learning. So it's like a multi-stage process where the model learns from both human examples and reward signals. And this approach seems to be working well for other large models too, like OpenAI's GPT models.
So a combination of learning from examples and then refining that learning through rewards. And what's the final approach?
The last one is pure supervised fine-tuning and distillation. The idea here is to use a large, powerful reasoning model to generate training data and then use that data to fine-tune smaller models. It's like a teacher-student scenario where the smaller model learns from the bigger model. This approach is interesting because it can lead to more efficient reasoning models, but it does rely on having that big, powerful model to start with.
So lots of different approaches being explored, each with its own pros and cons. Now let's talk about how we evaluate whether an LLM is actually reasoning effectively. The Beyond Accuracy Research Survey argues that just looking at whether the answer is right might not be enough.
Yeah, that's a really important point. They say that while LLMs are getting good at tasks that seem to require reasoning, we don't really know how they're doing it. Most evaluation methods just focus on accuracy, on whether the model got the right answer. But that doesn't tell us anything about the reasoning process itself.
So a model could be getting the right answer for the wrong reasons.
Exactly. And the survey suggests that LLMs might be relying on surface-level patterns in the data rather than true understanding or logical reasoning. So we might be overestimating their reasoning abilities because we're only looking at the outcome, not the process. They argue that we need better evaluation methods that can actually probe how the model is thinking.
And the Google research about using transformer models for graph-based tasks, that seems like an interesting way to test reasoning in a different domain. What was that about?
So in that research, they gave transformer models, the same kind of models that power LLMs. They gave them tasks that involve reasoning about graphs, things like finding paths between points or detecting cycles. And what's surprising is that the transformer models actually outperformed specialized graph neural networks, which are specifically designed for working with graphs. This suggests that these transformer models might be learning some kind of general reasoning ability that can be applied to different types of data, not just language.
So they're showing signs of being able to reason beyond just language. That's pretty exciting. Now let's talk about real-world applications. The Acera article had some examples of where AI reasoning is already being used.
Right, so we're seeing AI reasoning used in healthcare, finance, customer service, even legal and compliance. In healthcare, it's being used for things like medical diagnosis, treatment recommendations, and drug discovery. This is leading to faster and more accurate diagnosis, more personalized treatment, and faster drug development. In finance, it's being used for fraud detection, credit risk analysis, and investment insights. This is helping to reduce financial risks and improve decision-making. In customer service, it's powering more sophisticated chatbots that can handle complex queries and conversations, leading to a better customer experience. And in legal and compliance, it's being used for things like contract analysis, regulatory compliance, and case prediction. This is helping to speed up legal processes, reduce risks, and save money. And across the board, AI reasoning is improving decision-making, automating complex tasks, and enhancing security.
So even though AI reasoning is still developing, it's already having a big impact. What about the future? What are some of the challenges and innovations on the horizon?
Well, there are still challenges to overcome, like data dependency, where the quality and biases of the training data can affect the AI's reasoning. Explainability, where we need to be able to understand how AI systems are making decisions. Contextual understanding, where AI needs to be able to reason in complex and nuanced real-world situations. And there are computational limitations and ethical concerns to address as well. To move forward, we need to improve data quality, develop more transparent AI systems, enhance their ability to understand context, create more efficient algorithms, and establish strong ethical guidelines.
And what about future innovations? What's coming next?
Well, they talk about things like neural-symbolic AI, which we discussed earlier, and they see common sense integration as being crucial. They also predict the development of more dynamic learning models that can learn and adapt in real time. And they think there will be progress in cross-domain reasoning, where AI can apply knowledge from one area to another. And of course, there's the potential of quantum computing to revolutionize AI reasoning. In the future, they expect to see improvements in explainability, better human-AI collaboration, more personalization, more autonomous systems, and a greater focus on ethical AI.
So we've covered a lot of ground today. To sum it all up for our listener, what are the key takeaways from this deep dive into LLM reasoning?
I think the main takeaways are that LLM reasoning is a rapidly evolving field with a lot of exciting progress, especially with things like chain-of-thought prompting. But it's important to be realistic about the limitations. There's still a lot we don't know about how LLMs are reasoning, and it's possible we're overestimating their abilities. We need better evaluation methods, and we need to continue exploring different approaches to building and training these models. And while AI reasoning is already having a big impact on the world, we need to address the challenges and continue innovating to realize its full potential.
And with that in mind, here's a final thought for you to consider. Given that LLMs are so reliant on data and pattern recognition, how can we create training paradigms that truly foster abstract reasoning and genuine understanding? How can we move beyond mimicking human-like responses and get to a point where AI systems can think independently and logically, even in situations they've never seen before? That's the question that researchers are grappling with, and it's what makes this field so fascinating. Thanks for joining us on this deep dive.
It's been a pleasure.